So we can also obtain the frequency response of a system if we have the Z transform, if we replace Z by e to the power of j omega. So this is also the relation between Z transform and the DTFT that we've seen before. In this case, when we replace Z by e to the power of j omega, the formulas of both transforms becomes identical. And this is something like reading now the Z transform along the unit circle in the complex domain. So we also have a periodicity of 2 pi, and we have that for real valued signals there is a symmetry between the upper half of this circle and the lower half of this circle. So we have a complex conjugate symmetry in this complex plane. So by replacing Z by e to the power of j omega, we can compute the frequency response of our system, and we can have an example of this process. So here we have a low-pass filter as a moving average. So this is the equation for this moving average filter, and we know that a unit impulse is equal to 1 when n is equal to 0 and 0 elsewhere. So if we replace here the unit impulse, x will be the unit impulse, and then we will have our impulse response h of n, and it will be half and half. So we can see the impulse response also in a vector way. So it's good to point out that the discrete convolution operation can also be written as a matrix multiplication when we use a so-called Sylvester matrix. So if we change the shape of our impulse response vector in the format of a Sylvester matrix like this, and then we have convolution in terms of matrix multiplication. So we have our input vector, we multiply by the Sylvester matrix, and we have an output which is the discrete convolution. We can also change the shape of our input signal and multiply a matrix multiplication with the impulse response vector, and we still have the convolution. So we can have an example. I will use the impulse response the same as we have here, 0.5 and 0.5. And our test signal will be 1, 2, 3, 4, 5, sequence of numbers from 1 to 6. Here I'm creating the Sylvester matrix. So we have from our vector of impulse response, now we change it into matrix form using this so-called Sylvester matrix. And now if a matrix do a matrix multiplication with our test signal, which is a vector 1, 2, 3, 4, 5, 6, and we multiply by the Sylvester metric, and then we will have our output. And in fact, we can see that when we use NumPy convolve, so the convolution by the NumPy library, and we have this matrix multiplication, we have exactly the same results. So another example, not using the Sylvester matrix, but using this change of shape in the input signal, we will now convolve our sweep sinusoid that we used in previous example with the black box number 2 that we also used in the previous example. So this is a high pass filter approximation of a Chebyshev type 1 of third order with 3 dB allowance and ripple in the pass band, and the cutoff frequency was 8 kilohertz. So when we apply this matrix operation, so we're multiplying, we will change the shape of our sinusoid's sweeping sinusoid. So this is what we're doing here. And then we'll multiply with our black box vector. So it's the impulse response, and we will have our So if you remember the sweeping sinusoid, you've seen here that it removed the low frequencies from the sweeping sinusoid. And in fact, if we plot a spectrogram of the output of this convolution, we see that around convolution, it's cutting, attenuating the signals on the cut band, and then after the cutoff frequency, the signals are back to normal. So now we use here convolution as a matrix multiplication. So we can see the discrete convolution operation also as matrix multiplication.